All right, hey everybody. We are moving right along here to continue on with our work through concepts B7 through B9. To this point, you guys should have done a short section at the beginning where you did some fill in the blank notes at the beginning of your um, section on B7. Then what you should have moved on to is you should have ran through the lesson on voltaic cells and tried to get an understanding of voltaic cells. And where you should be headed next then is to this section here, where we're going to pick up and talk about something called cell potentials. And technically this is concept B8. Remember that we covered the beginning of B7, and then we're gonna shuffle our way back to that B7 again when we talk about electrolytic cells, which is the other kind of electrochemical cell that we're going to be worrying about in this section. This cell potential stuff gets a little bit mathy, but it's not too bad. There's one section in here, and I'll highlight it, where things can get a little confusing when we fiddle around with the reference half cells, but we can have a look at that. The math is relatively simple to do, though. It's working with what you see at the bottom here, a very simple formula that we need to deal with, and it'll have you going back into your data booklets to page 7 and playing around with those again. So we're going to work our way through this relatively painlessly, I hope, and continue to play around with what we know about cell potentials and get a better understanding of voltaic cells and what we can learn from this. I'm just going to do a quick pause. You won't even know it. And I'm going to switch where the display is of my ugly face, and then we'll go from there. So be right back. Alrighty, well, that didn't shift at all, so we'll just go with it. So standard cells and cell potentials. Cell potentials are going to give us an idea of, in general terms, how much electricity might be moving through a voltaic cell or an electrolytic cell, or what it might generate if we're dealing with a voltaic cell. Before we do this, I want to get into talking just a little bit about some of the some of the terms that we need to know as we move our way through this. So first thing we'll talk about is a standard cell. And before we go any further with that, remember looking back to Unit A when we were dealing with chemical reactions and what was going on with chemical reactions, we did talk about the word standard a lot. And the word standard just means that we're dealing with certain conditions. And so in this case, a standard cell is a voltaic cell in which each half cell contains all entities shown in a half cell equation at, and here are our conditions to make it standard, at SATP with solutions at a concentration of 1 mole per liter. So there is our standardization of that, okay? So when I say standard, that's what I'm really referring to. And you'll notice right here, there's that little degree symbol again that we used when we were talking about enthalpies to relate to those certain conditions. So a standard cell potential then is the maximum electric potential difference, what we'll call voltage, of the cell operating under standard conditions. So 1 mole per liter at SATP. A standard reduction potential, then, is the ability of a standard half cell to attract electrons. Remember, reduction is the gain of electrons. So the potential to get reduced, a reduction potential, is your potential to pull electrons towards you. Remember, of course, that when we're dealing with this section that we're dealing with now and throughout the unit, that the strongest oxidizing agent gets reduced at the cathode, and the strongest reducing agent gets oxidized at the anode. Okay, so we're gonna circle back to that at some point as well. So the standard reduction potential then is the ability of a standard half cell to attract electrons, thus undergoing a reduction. If a half cell with a larger, more positive reduction potential gains electrons, or sorry, the half cell, let me do that again. The half cell with the larger, more positive reduction potential gains electrons from the half cell with the lower reduction potential. In other words, we're going to be having our strongest oxidizing agent getting reduced and our strongest reducing agent getting oxidized. Very, very simple. It's what we've been doing throughout the whole unit so far. To calculate the standard cell potential of a particular voltaic or electrolytic cell, all we do is we take the difference between the reduction potentials of the two half cells. And in particular, it's always cathode minus anode. Okay, so C minus A. So whatever your reduction potential is for your cathode minus your reduction potential for the anode will give you the cell potential for that particular cell. So let's move to the next slide. It's impossible to experimentally determine the reduction potential of a single half cell. What that means is if you've got a brand new half cell that you've created and you want to figure out what its reduction potential is, you can't just sit it there and look at it because it's going to do nothing. Okay, it is either going to be the reduction or the oxidation half cell, but it can't work without the other half cell. So you can't have half a cell, you've got to have two half cells working together to make a whole cell. I hope that kind of makes sense to you. So you need to have a transfer of electrons, otherwise you're not going to end up with any sort of redox reaction taking place, right? Electron transfer theory says that we have to have electrons being lost by something and electrons being gained by something. So we need to have a transfer of electrons. Therefore, they need to be involved in an oxidizing agent and reducing agent relationship. And that's going to be very important. Luckily, what we can do is we can test the reducing strength of all half cell reactions in relation to what we call the standard hydrogen. Oh, I'm going to go back and I'll underline this with, I don't know, a color. So with what we call the standard hydrogen half cell. Okay, and that standard hydrogen half cell is what we tend to compare all of our individual half cells to. And that is what we call, or sorry, it will have an electrode potential of 0 volts, and we will call it the reference half cell. Okay, so if you've developed your brand new half cell that you're wanting to test out to see what its reduction potential is, what somebody would do is they would take that half cell and hook it up to a reference half cell, in this case the hydrogen half cell, and run it through, run that cell and see what our voltage registers as. So the standard hydrogen half cell consists of an inert platinum electrode. Remember, we talked about inert electrodes in the last video, where we said an inert electrode is an electrode that does not react with anything. It basically is there to provide a conduit for electrons to move along. Okay, so an inert electrode is something that isn't going to react at all. And this inert platinum electrode then is not participating in the reaction. It's immersed in a 1 mole per liter solution of hydrogen ions with hydrogen gas bubbling over the electrode. So it's actually a complicated little rig that they use to make it happen. And they keep the gas at SATP, so that means that it's going to have to be at 25 degrees Celsius and 100 kilopascals of pressure. And the reduction potential of the hydrogen reduction half reaction is exactly 0 volts. And so remember, on your page 7 of your data booklet, you have the hydrogen half cell. I'm going to shift it over there, sort of right in the middle of the page. And actually, what I'll do is I'll just remind you, I've got it pulled up here. Just have to remember where I put it. There it is. So what you have here, down in the middle of this page, if you recall, is the hydrogen half cell. And there it is, right inside the page there. Okay, so that's our reference half cell. And so that means that on this table here, all of these reduction potentials were all determined by comparing it to the hydrogen half cell, by reacting each one of those with the hydrogen half cell. Of interest to you, as we move through this, is that anything that is positive on here must have been the cathode, and anything that is negative down here must have been the anode when it was reacting with the hydrogen half cell. So that means here, for example, I don't know, copper, right? This copper half cell at plus 0.34 volts. What that means is this was the cathode, and then our hydrogen half cell was pretending to be the anode. And when we look at lead, for example, just down here at negative 0.13, that means that this was the anode and our hydrogen half cell was pretending to be the cathode. So the reduction, using the standard half cell, we can assign a reduction potential to every other half reaction that we want to compare it to. And so what I just finished saying, reduction potentials with positive values means that they have an OA stronger than the hydrogen ions, right? So that whatever, again, what we were looking at in here, whatever we were looking at for copper ion here is an oxidizing agent. And so that must mean that the copper ion is a stronger oxidizing agent than the hydrogen ion. Well, that certainly makes sense because it's above the hydrogen ion on the left side of the table. If the reduction potentials are negative, then the oxidizing agent of the half reaction that we are comparing to the hydrogen half cell is weaker than hydrogen ions. So looking at it down here with lead, right? Hydrogen ions are a stronger oxidizing agent than lead ions. So this is your cathode and this is your anode. I hope that makes a little bit of sense to you. So what we do then and how we can work with all of this knowledge is we can start to set up half cells like, voltaic cells like we did in the previous video and start to actually do some calculations to determine the voltage that's created, the cell potential that's created when we hook that particular cell up. This is just giving you an example of what we might do with one half reaction, comparing it to the standard or the reference half cell. So to measure the standard reduction potential of a half cell, we simply hook up that half cell to a standard hydrogen half cell and let it run. The measurement on the attached voltmeter between the anode and the cathode will tell us the standard reduction potential. So remember, this is our cell notation here. And just as a refresher, we always put the electrodes on the very outside. We know they're electrodes because they're solid. Electrode cannot be something aqueous or gaseous. That's not going to work. So, or liquid for that matter. And so we have a solid platinum electrode. There's our inert electrode, with the hydrogen being bubbled over that hydrogen ion or acidic solution. Then this double line, remember, means that we have our phase gap, not our phase gap, pardon me, our gap between the two beakers, and so this is creating that barrier, that porous gap, or that salt bridge or whatever it might be in that particular cell. Then we have our solution in the other half cell, and then our electrode in the other half cell. And if we hooked this up together, this would end up producing positive 0.34 volts on our voltmeter. That would be derived from taking, we would register what we'd have on the voltmeter, and we could substitute in the value we didn't know. Maybe we didn't know the copper here, so we would put that as a question mark or an X, and then we would solve, and we would figure out that it'd be positive 0.34 volts. Hope that made sense. If it didn't, track me down, and we can discuss it again. So, in the above example, copper is playing the cathode and is therefore the stronger oxidizing agent, and we need only look at page 7 of our data booklets that I showed you to see that copper is a stronger oxidizing agent than hydrogen ions. If we were to look at the aluminum standard half cell, we'd see something different. Okay, so I'm just going to jump back to that page and we'll find aluminum on here, and aluminum is right down here, a little further down, way negative 1.66. And you'll see then, all I'm trying to say in this slide is that half reaction is well below our hydrogen half cell, our reference half cell. And when we look at the table, we see the value for the reduction potential of aluminum is negative, indicating that it is a weaker oxidizing agent than hydrogen is. So I hope that makes a little bit of sense. Run back through this a couple of times, and if it still doesn't make sense, track me down at some point. So, if we wanted to write the aluminum overall cell reaction out, we would do the following. If we wanted to try to figure out how to do all of that stuff, here's what we would do. we'd write out the half cell for the anode, then the cathode. We'd balance and cancel electrons. We'd write the net equation, and then we would use, in order to calculate our cell potential, we'd use this, this formula. Remember that this is cathode and this is anode here. Page 629 of your textbook walks you through this in a really good way, I find. And I'm going to do a couple of examples here shortly that'll show you what's going on. A couple of notes to keep in mind that are very important and tend to crop up on quizzes and the diploma exam. Reduction potentials are not modified by the factors used to balance electrons. So when we get to the point here where we're balancing and canceling electrons, that does not change our reduction potentials. Okay, those reduction potentials stay as they're written in your data booklet. Okay, the second note here is that a positive cell potential, a cell potential that is greater than 0, indicates a spontaneous reaction. And remember, for a voltaic cell, all voltaic cells are spontaneous reactions, meaning as soon as you connect the wire between the two electrodes, we are going to start to get a flow of electrons along that wire from anode to cathode. I hope that makes sense. Okay, so if we have a positive cell potential, we know we're dealing with a voltaic cell and that the reaction is spontaneous. What that means then when we get into electrolytic cells in the next lesson is that the electrolytic cells are going to have a negative cell potential, and that is going to mean something a little bit different for us when we get there. So I'm going to do some examples. This is the first example, and I'm going to pull it up on the computer here and kind of walk you through what's going on. I took your advice, and I'm going to stick with the examples that I've written out by hand, and I'll sort of show you how I worked my way through it. So this one says a standard lead dichromate cell is constructed. Write the cell notation, label the electrodes, and calculate the standard cell potential. So I'm going to jump to, this is example number 2, so we'll jump to example number 1, and I'll make this nice and big for everybody, and maybe, maybe what I'll do first, hang on, is, I'm still learning the technology here, I'm going to move my ugly mug down into the corner here so that when I make this nice and big, you guys can still see my face and still see what's going on. So remember, this one is a lead dichromate cell that's being created, and so we've got 2 half cells in every cell. And so what I did initially is I just wrote down what I know. It's lead and it's dichromate. So you're always going to have your lead is going to be paired with its ion, and we're going to have our phase barrier here. This is our lead electrode with a lead solution. And then this is our salt bridge, and then we're going to have our other half cell. Now, because dichromate is an ion, we can't have dichromate just by itself. And we also know that dichromate only does its thing when it's combined with hydrogen ions, so I had to include the hydrogen ions in there. Since this is, there's no single metal ion in here, we have to include an inert electrode to allow electrons to move. And so you could choose either a copper electrode or a platinum electrode. Both are inert. If you put either of those on a test, I would be a happy camper. And so what I did then after that is I went through and did labeling of oxidizing and reducing agents. And in particular, I was able to say that lead is a reducing agent, and I started with that as a reducing agent. And then I labeled the lead ion as an oxidizing agent. I know that dichromate and hydrogen are an oxidizing agent, so I started with that. Hydrogen ions are oxidizing, and then these inert electrodes are neither oxidizing nor reducing. They are inert. They don't react. Where that took me then, when I went to my table, is I figured that this was the strongest oxidizing agent, gets reduced at the cathode, so this entity here, and that the only reducing agent that we had around was our lead, and that becomes our strongest reducing agent, which gets oxidized at the anode. So then I was able to label strongest oxidizing agent gets reduced at the cathode. So this is our cathode over here. This half cell is our cathode, and this half cell over here is our anode. What I did next, following those steps that we had on the previous slide, I went and I began to write out my half cells. So this is my cathode half cell and my anode half cell. I wrote them down as they appear in your data booklet, remembering to flip the lead because it's getting oxidized, not reduced. I needed to multiply the lead by 3 in order to make sure the number of electrons transferred was equal between the two. I wrote out my net reaction. Then the last thing I did is I took our formula that we've been dealing with in this section. I wanted to calculate the cell potential for this particular lead dichromate cell. I went into the data booklet where I found the half cells, and I referenced that the dichromate half cell has a reduction potential of positive 1.23 volts, and I subtracted that from the negative 0.13 volts of the lead half cell. One little note for you, and something that I like to do just to keep my brain straight on everything, is I like to throw brackets around each of the half cells just so that I remember to notice the sign for each of these, because this becomes positive 1.23 minus negative 0.13. So that gives us positive 1.36 volts. If for some reason you missed the minus negative, you would end up with actually a number that wouldn't work out. So that's why I put those brackets around there. Just a personal thing to remind me about what's going on. I wanted to make this note here, and I put this down here for us, that this is a spontaneous reaction because it is a positive cell potential. We could also then conclude that because it's a positive cell potential, it is a voltaic cell as well. So when we hook this up, it would start to result in a flow of electrons from the anode to the cathode. So I hope that example makes sense. If you need to pause right now and go back and have another look at it, that's totally cool. What I'm going to do is jump back to the PowerPoint, and we'll go on to example 2. So example 2 says a standard scandium copper cell is constructed and the cell potential is measured. So now we've got our standard scandium copper cell, right? And we've listed it out, and I'll show this on the diagram that I drew up for the question later. And the voltmeter indicates that the copper electrode is positive. Okay, that's key. When you know that an electrode is positive, that means it is the cathode, as long as we're dealing with a voltaic cell. And we haven't covered electrolytic cells right now, so we are not going to worry that it's an electrolytic cell. And they've given us what the cell potential is, not the reduction potential, but the cell potential. Now we're going to write and label the half reaction and net equations and calculate the standard reduction potential for the scandium ion. That's the one we don't know anything about. So I'm going to jump back and we'll do example 2 here, which is the one we're working on next. I'll make it nice and big so that everybody can see. So what I've done on the top here is I've recreated that cell notation that they gave us in the question. Through the positive out in front of there, or through the cell potential out in front of there. And then I made the note to myself, the copper electrode is positive. It tells us that in the question. So that means then that the copper electrode, that this half cell is the cathode. What that then means is that this half cell is the anode. Hope that makes sense. That jump, if it tells you that an electrode is positive and we're dealing with a voltaic cell, then that means that the positive electrode is the cathode. Where we move on to next is I wrote down my two half reactions. The copper is at the cathode, and so cathode is where reduction takes place. That's where our strongest oxidizing agent gets reduced. So I wrote my reduction half reaction, and then I wrote my oxidation half reaction below that. I noticed that the electrons transferred is not equal, so I had to multiply the oxidation half reaction by 3 and the reduction half reaction by 2 to make sure that we had a total of 6 electrons transferred for each. And then I wrote my net reaction down here. Then this is literally the tricky. And I summarized my reduction potentials and cell potential here. This is the hardest part here, I think, and it's really not that difficult, and it looks a little messy on here. Where I started is our cell potential is equal to the reduction potential of the cathode minus the reduction potential of the anode. but we are interested in the reduction potential of the anode. So I rearranged my equation using algebra. First thing is I wanted to get rid of this negative from the anode and get it by itself on one side. So what I did is I added the reduction potential of the anode to both sides. That eliminated it from this side and popped it over here. Then I had to get reduction potential of the anode by itself. So I did the opposite of addition. I subtracted the cell potential from this side and from this side, which canceled out those. So the reduction potential of the anode is your reduction potential of your cathode minus the reduction or the cell potential. So that was positive 0.34 volts minus positive 0.236 volts. And remember, I put those brackets there just to remind myself that we're dealing with positives and negatives here. That gave me an answer of negative 2.02 volts, which means that it is non-spontaneous because we have the negative right here. That also is going to indicate to us later on that we are dealing with an electrolytic cell, but we haven't covered electrolytic cells yet, so don't stress on that too much. Okay, that's both examples. I hope that made sense to you. If they didn't, then please make sure you track me down in office hours or at some other point so that we can have a conversation about what might not be making sense. I also wanted to just really quickly talk to you guys about corrosion, and I put this on here even though you may not be writing a diploma this year. I still think this is important and it does pop up. It's not strictly in the curriculum, but we tend to like to ask questions about this. So I'd like you guys to take the time once you finish watching this video to just quickly open up your textbooks to page 634 through 636 and just read the little bit about what they have in there about corrosion, the rusting of iron, corrosion prevention, including things like protective coatings, cathodic protection, sacrificial anodes, all of those kinds of things. I think they're important to understand, and it gives you another practical application of what we know about these particular redox reactions and what we can do with them. Okay, so this wraps up concept B8. Which is what we've been doing right now. So I'm going to encourage you guys to go and do LSM 14.2i, and you can always double check if you forget that back in the Google Classroom where you found this video. There's a document in there. You can refer to all of the practice stuff you want to do. I would go and do that and see how it works for you. If you have any questions, track me down during office hours, fire me an email. We can get online and chat about things. And other than that, what's going to happen is you'll have one more video after this that is going to include, because this one's getting long, is going to include a discussion about electrolytic cells, and then I'm going to bring in B9, which is talking about the similarities and differences between voltaic and electrolytic, as well as talking about something called the chloride anomaly. So yeah, we're at almost 30 minutes, so I'm not going to do another 15 or 20 minutes on this. So go ahead, do the cell potential. Go ahead and do the cell potential worksheet, and then when you feel like you're ready, fire up the next video on electrolytic cells. And that's all I have to say for now. Stay healthy, take care of each other, and we will talk again real soon.